22 degrees.
22 degrees Celsius here in the room. Okay, remember that because you're going to use that measurement to find the lowest possible temperature in the entire universe.
The lowest?
The lowest. First, you're going to start with 22 degrees in this room. You don't sound like you think I'm going to do it. You will. You just watch. And you also have to find the pressure of the gas in this metal ball down here. And see, it's connected to a pressure gauge up here. That's pounds per square inch.
Pounds?
Pounds per square inch. Yeah, that's a measurement that they use in some parts of the country that are not in the metric system. So give the thing a tap like that to make sure the needle is loose. Now what do you read?
I read 14.5 degrees.
Okay, 14.5. Now you've used graphs in school.
Right.
So here's the graph over here. Notice along the bottom, temperature, right? Along the side
is the air pressure.
Okay, so now you use the red pen and put the dot where what was the temperature?
22.
22 and 14 something.
5.
Okay, right in there. Very good. Now we have 1 point on the graph. Now come on over here because now we're going to do the same thing with ice water. And so read, I have a thermometer in there already. What does it read?
It reads just above 0. So
it should be 0 correctly, right? Because that's the temperature at which Celsius is calculated, right? Okay, so now what's the pressure?
The pressure is just...
Did it go up
14.
or down?
It went down.
Right, it went down to what?
It's at 14.
Okay. 0 degrees
and 14.
And 14. Put that on the graph. Okay. Now we're going to measure it in hot water. So come on over here on the stove. See, I have water that's beginning to boil. And what's the temperature of the water at the moment?
It's just 92. 92.
If it were boiling, it'd be 100, right?
Right.
But it's not. It's 92. So remember that. And now what's the pressure?
The pressure is going up from 14 or 17. It's 17.8.
17.8?
Yes. Oh, now it's 18.
Okay, 18. Okay, so we got to put that on the chart.
So it's 18.
18
is the pressure.
Okay, so yeah, the pressure was 18.
92.
And the temperature was 92 or something, you said?
Yes.
92 and 18 about like, okay. Very good. Now we're going to do the same thing again with this dry ice bath. It's dry ice in alcohol.
Why is it bubbling?
Well, it's bubbling because some of the carbon dioxide is coming out of the dry ice. So put on the safety glasses. So we're just to be on the safe side. And then I'm going to put in the thermometer, and I want you to watch a very interesting phenomena. See what the temperature is now? Watch.
Whoa, it's going down really fast. Now it's way off the scale.
Yeah, it's going off the scale.
Now it's going hot.
Yeah. It looks like it's hot. Well, obviously it went way past 0 because the scientists have measured the temperature of this bath and found it's minus 78. Okay, so remember the temperature of the bath is 78, minus 78. Now comes the pressure.
It's going down.
See
How come you have to put it in so slowly?
Well, the reason is because I'm boiling the liquid. The metal ball is so hot, it's boiling it.
Well, then how come there's cold on the outside?
Well, it's cold on the outside because the air in the room had moisture in it. When the air came here next to the beaker, it deposited the moisture from the air.
Oh, so it's like snow.
Yeah, it's like snow. Okay, now it's probably settled down. What's the reading of the pressure?
It's 11.
Okay, so you want to put that on the chart.
So 11 and
minus 78. Right.
There's 11. There.
Now, when you've done graphs, you've been able to sort of join all the lines together and extend it both up and down. Let's try that with this. Here's a straight edge. Let me hold it for you over here. And what do we got? That one's a little low, and these are two a little high, so it's about, let's just say it's about like that. Does that look like about to you? Okay. What happened to the pressure?
It went right down to 0.
And see what happened to the temperature?
It's just
Well,
above 300.
it's a little above, or it's above 300. As a matter of fact, when scientists did this, and they got down to a 0 pressure, they found the temperature was minus 273 degrees below 0 Celsius. That is absolute 0.
It's the coldest anything
That's as cold as anything can get. Yeah, that's why it's called absolute 0. And it's also called the Kelvin scale after Lord Kelvin, who designed it. And scientists have tried to get it that cold, and they come very, very close. But after all, the thermometer wouldn't read when it got that cold because the molecular motion stops, and that's what temperature is. And all kinds of strange things happen at those low temperatures. Anyway, you can tell people proudly that you have calculated absolute 0.
Absolute 0.
Right. Okay, Andrew, in order to have a fire, you need 3 things. Heat, the supply of fuel, and oxygen. Certainly, we got enough heat. I got a blowtorch here, and there's wood inside there. So what must be missing?
Oxygen.
Oxygen, right. Okay. Now notice, we're changing the wood into a gas, and the gas is coming out here. So are you ready with the match?
Yep.
Okay. See if you can light it. Okay, now you can take the match away. Now notice that we're burning the wood after it's changed into a gas.
It looks like the fire's burning the smoke.
Right. Okay. You want to blow out this? Okay. Now I'm going to move it out of the way so we don't get that smoke. And you can take your safety glasses off.
Okay.
Now, Andrew, the reason I wanted you to see that is because today we're going to see how to start and maintain a campfire or the fire in a fireplace.
Yeah.
Okay? And here's our campfire right here in miniature.
Yeah.
Well, you don't want to start a great big campfire inside, but even though we're dealing with a very small fire, notice I have it on sand, which is fireproof. Back there is a fire extinguisher. And I even have a fan standing by in case it gets too smoky, we could open a window and blow out the smoke.
Yeah.
Because I want to do it in miniature so that you can sort of see what happens. Notice there's paper down below and then little sticks here. Now you know how to light a fire?
Yeah.
Of course. Okay, why do you start out with things like paper?
Well, because paper burns easy.
Right, and you could do shavings or sticks all kind of shaved up. Okay, try lighting it, go ahead. Okay. Okay, now why the little tiny sticks?
Well, because the little tiny sticks would burn easier into a gas than the big sticks.
Right, than the big one. Every time, almost went out. Every time you're having a fire and a flame like that, it means some kind of fuel has been changed into a gas. Now, as it gets going, see if you can notice any place where there's sort of a jet of gas coming out, and you'll notice that that's usually where the fire occurs. How are we doing? Okay, still, here it comes now. See right there, there's a little, see that flame coming up?
Yeah.
Okay, now there's another one up here. See that smoke coming out? Okay, now sometimes the sticks are close enough together to heat each other, and that causes them to change it into a gas, but there's not enough heat to catch it on fire. So that's why it sort of smokes. And you know what happens when the wood is wet?
Yeah.
Yeah, it smokes like mad because it's too cool.
How come when the sticks move when
Well, you can see
fire?
if you've changed it from a solid into a gas that some of the parts are being changed and gotten rid of, so to speak, so that makes them change. Here's a little nice gas coming out here. Look at the end over here. See how it's burning it? So that eventually you can get a big log burning, and when you get a big log, notice across the top sometimes you can see real streamers of gas coming out because the log has been heated enough to change the wood inside to a gas. Okay, now whenever you have a campfire, at least you should make sure it's out. How would you put that one out?
Well, maybe spread it out.
Okay, there's a stick, spread it out.
Put it with sand or maybe wet it.
Yeah, well, how come spreading out sort of puts out the fire?
Well, because it needs
Wait a minute, you have plenty of what? Fuel,
fuel.
plenty of oxygen.
Yeah, but it needs heat.
Yeah, so you're spreading it out to keep each one of those kind of cool. Then you could stomp on it, right?
Yeah.
Which would smother it to get rid of the supply of oxygen, or cool it off with my special fire extinguisher.
Okay.
Okay, I hope now you'll know how to start and maintain a campfire.
That's neat. How does it do it?
Well, first of all, what do you mean by neat? All you kids use the word neat.
Interesting.
Is what, interesting?
Yeah.
Okay. Well, you can make this sort of swirling colors at home by using simple ingredients, and it'll go on, there it goes, it'll go on like that for, half an hour, and you can then revive it again and get beautiful colors. So here's how to do it at home. First of all, get a tray or a dish of some kind.
Yep.
Like this. And here, Dan, would you add milk?
All right. Here you go.
Okay,
There's
now
milk.
put a drop of food coloring right near the edge. You have green, and I'll have blue. Okay? You put red back there, and I'll put yellow over here. Now, have you heard of the term surface tension?
Yeah, that's kind of something that goes over the surface.
Yeah, that's water and in this
Yeah.
case milk and whatnot have a sort of thin skin over the top because the molecules are packed together, and it's called surface tension. And soap, which is the next thing we're going to add, breaks the surface tension so that the tension that's left pulls away from where we put the soap. So that's what makes the colors sort of blend. So I'll put a drop of soap down the edge like that. There we go. There goes.
Looks like a mushroom ball.
Yeah, that was a mushroom. Here goes the blue side. I put some over here in the yellow side.
There it goes.
And finally over here on the green side. And now, as the surface tension is broken, the colors get all mixed up like that. So anytime that you want to make your own version of moving modern art, get a tray, put milk in it, use food coloring, and finally a few drops of soap, and it'll go on for hours. Shan, before you leave today, I'm going to have you pour the liquid in this flask into that little beaker.
It's not going to fit in that little beaker, though.
Well, you wouldn't think so, but as a matter of fact, it will, I hope.
How's it going to do that?
Well, you'll see, because we're going to investigate a very strange form of saturation. You know what that is?
Nope.
Well, here's an example of saturation. I put some salt in here and stirred it up and let it sit, and you can see what's happened at the bottom down there.
Yeah, some of it's dissolved into the water and some of it's still sitting at the bottom.
Yeah. Now that means that the liquid is saturated because it's holding as much of the salt as possible. Now we're going to go to supersaturation. So take the spoon, take some of that stuff and put it in here. That's not salt, by the way.
It's all
Water stays
dissolving.
clear and it's dissolving.
You must need more of this to make it
Yes, as a matter of fact, you can put all of that in there because it's a very unusual chemical. See if I can explain it this way. Here's the sodium chloride. You recognize that?
Yeah,
salt.
salt.
When you put it into the water, it breaks up, and then eventually the water holds as much as possible, and the rest of it sinks to the bottom. But that other chemical is this.
Sodium acetate trihydrate.
Right. Here's the formula down here, and notice that there's what this is right here.
Water.
Water.
What does this little dot mean?
Well, the dot means that the water is really part of the crystal. It's not chemically bound up. As the crystal forms, water molecules get caught in there, and they're part of the crystal. So when you heat up the crystal, it dissolves in its own water.
Oh,
Then if
okay.
you let the solution cool down and you put it into a flask, you have a
into that.
supersaturated solution, which means what?
That means it's holding more than it should.
More than it should.
Okay.
However, look at the bottom of that little beaker.
There's little tiny crystals.
Yes, that's little crystals of this. So as you now pour it in here slowly, as soon as the first drop of liquid hits the crystal, it's going to start to solidify.
Okay.
And then slowly pour it in there, and you will see what happens with the strange solution that's supersaturated. Up, 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 up.
Holy, how did it do that? It's all
Well,
warm.
I did that because it all came out of solution. Yeah, see, it's solid.
Yeah,
Yes,
it's like a rock.
yes. Notice it's warm?
Yeah.
Well, that's because the crystals in solution were moving around real fast because they're in a liquid form. And now when they're in solid form, you're slowing them down so the energy has to be given off somehow.
And
It's
then
given off as heat. So there you had your first experiment with a supersaturated solution changing into instant crystals. Clara, I don't assume you've ever plated anything, have you?
No, I haven't.
Well, it's kind of fun to do. Kids like to because they can copper plate things relatively easily.
Okay.
In fact, here are some things that I've already copper plated. See, here's a key. That's what it looked like before I copper plated it. And there's what it looked like afterwards. So you can make a key stand out on your key ring
Yeah.
by copper plating it. Or here's a clamp. That's what it looked like before it's copper plated. And here's what it looks like afterward.
It's copper now.
Yeah, it sure is copper. And here's what you're going to plate. An iron eye bolt.
Okay.
Now what you need is first of all a supply of copper, but in solution. So here's the copper in chemical form. We'll put it in that glass.
Okay.
Nice blue color.
Yeah.
Copper sulfate. Okay, now add about enough water to fill it up about 3/4 of the way.
Okay.
Okay, good. Here's a stirring rod. Now stir it up.
Okay.
It dissolves fairly readily. But you see, what we want is a supply of copper in the solution, in the water,
Okay.
free to wander around. Then we need a supply of copper to go into the solution after we've taken some of them out. And here is our supply of copper.
Okay.
Copper plate. Okay. I'll connect it up to this red one and put it on one side like this. So now you take the eye bolt over there,
Okay.
okay, and connect up the other side. Okay, and put it, and don't let the two of them touch.
Okay.
Okay. Whoops. Now, that could be a key or a nail or anything else that you want to coat with copper. Okay.
Okay.
Now, not much is happening because we don't have any electricity going through there yet. So now what I'd like you to do is to turn on the current. Right there. Turn it up.
Okay. About there.
And I'm going to stick this string right in between so they can't touch, okay?
Okay.
Now, what's happening is the copper that's in the solution, as the electricity goes through the solution, it's pulling it out of there and depositing it on the eye bolt.
Yeah.
Okay.
Okay.
And the current coming from the other side is taking copper from the copper sheet and putting it into solution.
Okay.
Now, the same idea has been used when they coat other things. You mentioned silver plating.
Yeah.
Well, come on around right here. I have a sample of silver plate. And it was put on this spoon in the same way. Put
Yeah.
into solution, and gradually it built up a whole layer of silver.
Okay.
How about the ring?
Well, I guess it's gold-plated?
Gold-plated, yeah, and
Yeah.
done in the same way. You've seen this before, haven't you?
Yes, I have.
In what, Venetian blind?
Yes.
Yeah. Whenever something is real shiny like that, you can suspect that it's chrome-plated.
Okay.
Now, how about the bumper of a car? Real shiny?
Yeah, it's
Yeah, it's chrome-plated also,
Yeah.
yes. Then if it's plated, but not quite as shiny, you can suspect that it may be nickel-plated.
Okay.
Here is one that's plated with zinc.
You can see little
Yeah.
crystals.
Yeah, you see all the little crystals in there?
Yeah.
Now, the reason why they coat things with these metals is because they want to make it impervious to the atmosphere and to the rain and whatnot. That's why they coat the bumpers of the cars. That's why this has been coated with zinc so it won't rust.
Okay.
Now, we're coating our eye bolt over there just because we want to make it look pretty.
Yeah.
Okay?
It's black.
Well, it's all here. Turn off the current first of all.
Okay.
Okay. Now you take the eye bolt. Okay, and dip it in water to wash off all that stuff. Okay.
Okay.
Now it's black because as we took the copper from the solution and put it on the eye bolt, we were doing it in elemental copper, real little tiny pieces, so it doesn't reflect very well.
Okay.
So now after you wash it off, wipe it off with the napkin. Call it a napkin, it's really paper towel, right?
Yeah.
Here. There, you can begin to see it, see it?
Yeah, it's copper now.
Yeah. We'd leave it on a little longer, it would get more and more copper plated till finally it would be really thick.
Okay.
Okay. So you can take this home as a sample of the first time that Clara has ever plated anything. There you are.
Thank you.
There you see, we're cooking a hot dog in its own juice by electrocuting it.
Not barbecuing it this time, a new way to cook a hot
A
dog.
new way to cook a hot dog. Now we're sending electricity through it, so I'm going to turn it off. Because current is coming through it from the regular household current. When you turn on this master switch and that red light goes on, you have to be very careful because we're sending now regular 120 volts through the, over here to the fork, through the hot dog, over to the other fork and back here again. So we're playing with live electricity, like sticking your finger in a socket. So don't try this at home. See, unless your dad or your parents or your teacher or somebody's around, because it really is very dangerous.
Okay.
Now, the reason it cooks is because there's salt in the hot dog, and that makes it sort of a partial conductor, and then because it's not a really good conductor, it heats up the hot dog
And cooks it.
and cooks it, right. Now, a bunch of science teachers were at a summer camp one time, and they were doing this sort of experiment, and they thought, I wonder what else we could run electricity through and what would happen. So they went to the refrigerator and came back with that.
A pickle.
Right. A kosher dill pickle. So they put the forks in the end just like this, and this time I would like you to carefully turn on the current. Throw the master switch right there.
And the pickle has quite a bit of salt in it,
Yes,
too.
has quite a bit of salt in it, so they expected that it would conduct electricity, but they were in for a bit of a surprise, as you will see. Beginning to heat up. See how it's steaming over here?
It's all lighting up.
Right. See how it's...
Oh, and the smell. It's not the
Now,
best
this was a
smell.
big surprise. That not only did
Look
it
at
heat
it.
up, but it also arced like that.
It's making an arc and making light.
Okay, I'm going to move this over.
Whoa, when it goes in and when you pull it out, it makes a little current.
There we go.
Holy.
Now, this yellow color is due to the sodium ion that's in the salt.
Oh, yeah.
And when it's excited, it sends out that color. In fact, some scientists at a Kentucky university checked it and found out, sure enough, that it was the sodium ion.
Wow.
Then, if you look, you know, scientists look in the literature to find out if anybody has done the experiment before.
Yeah?
And they found that a German chemist way back in the middle 1800s had run electricity through salt water and vinegar, and he found this reaction. So it was called, after that scientist, called the Kolb reaction.
The smell just keeps getting worse. the
Yeah,
more
getting
it
worse and
goes in.
worse, right.
Yep.
Okay, because you know Steve Jacobs, my
Yeah.
friend, you know,
Yep.
everybody calls him Jake.
Yeah.
Well, he's the one who showed me this. So if they can call the original experiment the Kolb reaction, I think we ought to call the one with the pickle the Jake reaction.
Yeah.
Don't you?
I think
Okay,
so,
so
too.
turn it off. Now, don't try this at home, remember?
I won't.
Because it is very dangerous. You're working with live forks with 120 volts going through them. It could be very dangerous. But now that we're under this control, you can be the only kid in the block to electrocute a pickle. Go ahead, turn it on.
Thank you for the honors.
There.
Wow.